so we're going to start with proteins. And so in amino acids, you're going to have 4 different groups normally: a hydrogen, a carboxylic acid, a variable group, and an amino group. And so because it's around a chiral carbon, right, 4 different groups, there's going to be 2 different ways we're going to distinguish between them. So we're going to use D and L is how they're normally distinguished. So to determine whether it's D or L, a nice little trick is to remember corn. So the CO from the carboxylic acid is going to be the first part, and then your variable group is going to be an R, and then the amino group is going to be the N. Now the trick is if corn is being spelled to the left, then it's going to be an L. And then if corn is being spelled to the right, it's going to be D, because remember, D can become R if you just extend it a little bit. And then, so almost every amino acid is chiral. We do have an exception, which is glycine. And glycine is not chiral because it has 2 hydrogens instead of 2 different groups there. And so the one that's going to be found in nature is going to be the L group, because L is just lovely. And that's a very pro thing to do. Yep. Okay, so for lipids, fatty acids have a carbon double bond. And so we remember from topic 10 and 20 that there's going to be 2 different ways. You have the cis and the trans. And so cis is the one that's most commonly found in nature. So remember that. And then, so a lot of the times, the cis is going to be hydrogenated so that it can have a longer shelf life as a solid or a semi-solid or something like that. And so this happens when you have the cis and then you add hydrogen plus a transition metal catalyst such as nickel and 180 degrees Celsius. And what this is supposed to do is saturate the fatty acid completely, and saturated fatty acids will have stronger intramolecular forces. But what happens sometimes is incomplete hydrogenation. And so what's going to happen is the cis is going to transform into the trans. And then this is bad because the trans fats are going to increase the amount of LDL cholesterol, which is bad. And so the one difference between them is because cis is the same, it's going to look more like this, and then there's going to be the double bond, and then it's going to bend downward. And that won't stack as easily as trans, which is just a straight line. So trans is going to have a higher boiling point. Okay, so for carbohydrates, we're going to have the D and the L forms again, and this is, remember earlier, so we're going to have the hydroxyl. It's going to point to the right, so it's D, and then it points to the left that way, so L. But then we also have the ring forms with the carbohydrates and the sugars, and it makes it very complicated. So alpha is going to be on the bottom, and beta is going to be on the top. And if you want to think about it, the beta kind of makes a line going upwards when you're drawing it, right? And so that's why it's going to be up on the top. And so this is for glucose. And the only thing that changes with fructose is you add another carbon where this H would be. And so this is going to become the second carbon where the hydroxyl group matters when you're determining whether it's alpha and beta. And then inside of glucose, we have 2 different forms. We can have like the alpha and then we have beta. And so starch is the alpha form of glucose, and this is going to have O's that are going down as they bond to each other in the glycosidic links. And then cellulose, it's going to be alternating like this. So starch is going to form a very compact and spiral structure, and it's going to be digested by humans. And then we have cellulose, which is going to have alternating hydroxyl groups, right? Because remember, the alternating is going to switch what's up here. And so this is going to, because it's alternating, it's going to allow it to form hydrogen bonds, which is going to make it stronger. And it's going to lay flat instead of as a spiral, which is going to help it be a better structural component. And because it's stronger, it's not going to really be digested by humans. And so it'll travel along the little digestive, or the intestines, and then it's going to abrase against the walls, and it's going to help create mucus, which will help things, or feces, flow smoother out into the toilet. So that's why it's used a lot as a dietary fiber. Okay, so and then with vitamins, mainly what we're going to focus on is the visual cycle. So this involves vitamin A. And so vitamin A is called retinal. And so here we're going to see 11-cis-retinal is what we're going to start with. So this is one isomer of it. And then remember, in your eyes, you have rods and cones. And so think of the rhodopsin that's used in this visual cycle, and then the rods in your eyes. And so basically what's going to happen is this 11-cis-retinol is bonded tightly with opsin, and then when light energy comes through, it's going to change the isomerization to all trans retinol. So you can see they alternate now instead of being the same. And then this is going to dissociate from the opsin, and then this dissociation is going to cause a nerve impulse, which will help you to see. And then basically an enzyme is going to convert the all-trans retinol back into 11-cis-retinol, and then it binds back with the opsin, and it happens all over again. So this is the visual cycle. So B6 is a lot about xenobiotics, which are chemicals that don't belong. Think if the X is crossing them out because they don't belong. So xenobiotics can come through like urination, so female estrogen or other drugs can be excreted through the waste and they go down into the sewage treatment, but sewage doesn't get it all, and so it'll go into the environment, and things like fish will absorb these nutrients and they could become feminized, and then they won't be able to breed, which is really bad. And then we also have something called biomagnification. So if we take a substance like DDT, which is a big xenobiotic, and it comes in bug spray, and so what'll happen is it'll get absorbed by things like plankton, and then the plankton will be eaten by fish, and a lot of plankton is eaten by fish, so it multiplies, and then a bunch of fish are eaten by eagles, and so the eagles are at the top of the food chains, and are at the top of the food chain, and they'll be much worse off because they'll have so much more of this DDT in them than the normal ones, and that's what biomagnification is. Then we have things like oil spills, which normally aren't bad, but because of the concentrations, they become bad. And so we have enzymes or other micromolecules are able to break down certain parts of the oil and oxidize them into chemicals that are, or substances that are natural to the environments. Other ways we can remove xenobiotics are through host-guest chemistry. So this is where we have the xenobiotic gets encaged by a host, similar to how an enzyme attracts a substrate, except this is non-covalent. And that's very important to remember that. And it cages it in through other intramolecular forces. And then we have green chemistry, which is helping the environment through different ways. So like we have energy for enzymes for cosmetics, and it'll decrease the temperature we need, and we don't need to use sulfuric acid, or enzymes for detergents, increases the efficiency at lower temperatures. And then for biodegradable substances, we have things like starch, which will easily break down in the environment, and then they can be further broken down into carbon dioxide and water, which is why they're called biodegradable.